Hello, okay, let's start. My name is Timo Drick. I'm an Android developer at 7 Principles, and I will demystify pixel shaders today with you. I live in Frankfurt. Here you see the skyline. It's located in Germany. And I do Android development since many years now, I think 13 now. I will first show a short introduction. What are shaders, and I will also show some samples, what you can do with shaders. And then we go into the integration into Compose, how we can use shaders in Compose. The next chapter would be then draw simple shapes with shaders. And then we do animations. And at the end, I will show a little bit about the development process and compatibility things. And then we have a short summary. All slides are also available in the web. Here's a QR code. I will show this code again at the end. So you don't have to take pictures. Everything is available. And also the source code of everything should be also available. So let's see what we can do with shaders here. We have an app, and as you can see, the background, there are triangles and some different colors and stuff, and this is drawn by a shader. Here's another sample of some waves as a background. And here's the Jetpack Compose sample from the Android developers, jet lagged. And here you see also a shader in action at the top. It's also an animation, it's an animated background. We can also do animations for buttons, for example. When we want to advertise a button for the user, for example, we can do a shine animation. It can also be used to show loading animations, for example. And of course, I do have also an AI slide. I think all of you now programming an AI app because of the competition from Google, where you can win this DeLorean, and then you can travel back in time. But of course, you need also a visualization for this AI. And you could do this with a shader. For example, this one. Anyone knows how this AI is called? Yeah, right. Okay. And of course, we can also go crazy. For example, when it's a very important button or a hot button, we can animate a flame with a shader. It's also possible to do some 3D animations. It's all done with a shader. Or we can do transitions between two different composable screens. So shaders are used in almost any graphics pipeline today. And this AGSL, it's Android graphics shader language, allows us to use custom shaders in the Canvas API from Compose and also from the legacy Vue system. Shaders are also used a lot in games, and yeah, you can use it in OpenGL and also in Metal from Apple. And in iOS, it's also supported, not AGSL, but shaders in general. And in the web, you can use WebGL to draw shaders. Very important thing to note here, shaders are compiled and then executed on the GPU, so they are very fast. So let's see. I think all of you know the normal canvas draw operations, like draw a circle, and then we can fill it with a solid color, for example, or we can use a linear gradient to fill it. These are also built-in shaders. You can just use it. There's also a radial gradient, or you can use an image as a shader for the content of the shape. But today we will program a custom shader, and yeah, it's a complete different language. It's not Kotlin, as you can maybe see, but in general it's very simple. So you just program one function, and the input of the function would be the x and y coordinate pixel position of the screen. And you have to calculate then the color of this position. So you return the red, green, blue, and alpha value of the color. Yeah, the language, as I said, it's not Kotlin, it's more like C, but it's it's a completely independent language. It's it's more or less like AGSL. Here you see this main function gets a float 2 with the rect coordinate, and there we have the x and y position, and then we return a float 4 which contains 4 different values for the red, green, blue, and alpha channel of the color. Important also, the range is from 0 to 1. So 1 means full color. In this case, we have 1 at the red channel. This is why below this canvas is red. When we, for example, now, let's assume the canvas is 200 pixels in width. And when we now divide our pixel position by 200, then we get a linear gradient from 0 to 1, from left to right, as you can see here. And now some other things. I showed you this float 2 value. It's like a vector with 2 components. You can also write vec2. It will also work. There's also a float 3. Then you have 3 values. And you can access the different components by using the variable name and then .x, .y, .z. Or when you have a float 4, there's also a .w. If you want to use it as color, you can also use other accessor functions. It's then .r, .g, .b, and .a for the different color channels. So let's see how can we use this in Compose. So first of all, the shader code itself, we can just put into a variable, in a string variable. If you use this add language notation, then Android Studio will also do some syntax highlighting for the code. And then in our Compose code, we can create a modifier. In this case, I called it background shader. And I will provide then this string as a variable here. Then we use the normal draw with cache operation. You can also use other draw API functions. And then here's the magic. So in line 4, you see we create an instance of the runtime shader, and this will get the shader code and compiles it. And then we create out of this a brush. There's this function shader brush. And then you can use this brush in your own draw behind method. And for example, draw a rect. This will then draw the rect on the maximum size of, or available size of the canvas. This modifier then you can use in your composable. For example, this shader screen. We have here a box with fill max size and then the background shader. This will then look like this. So in this case, we just have this red background. Of course, the canvas size will vary depending on the screen or on the size of the composable. So if you want to get some values from our Compose code into the shader code, we can use uniforms for this. So we define one uniform in our shader code. It's called uniform float2. I called it size. So we define the type and then the variable name. And in the Compose code in line 10, we can then set this float uniform. We have to provide the name of the uniform and then the different floating point values. In this case, I just provide the width and height of the canvas. And then, as you can see below, we have this gradient from the beginning, and it will adapt to the screen size automatically. So, but of course, this is very boring. So let's see how we can draw simple shapes. For this, we need a distance function. So we have the position of the pixel where we need to calculate the color for. So we need a function where we give the coordinates of the current pixel, and it will return the distance to the outline of the shape we want to draw. The simplest shape would be a circle, and the distance function would be the length between the two different points. So it's just the length of the vector. So when we subtract our position from the vector coordinate, then we get the distance to the center of the circle. And when we subtract the radius from this, then we get a circle what it's not just a point, but with a radius. Here you see the code. So let's assume the canvas is exactly 200 by 200 pixels. Then the center would be at 100, 100. Let's define the radius as 100. So the circle will fill the whole canvas. And then here you see the distance function. And when we have the distance, we can just check if the distance is smaller than 0. In this case, we show the foreground color. And in the other case, we show the background color. Maybe you also noticed that the circle is very pixelated at the edges. Therefore, in shaders, we can use the smooth step function. So we have to define 3 different parameters here. It's the starting point and end point, and then the input value. And the smooth step function will map between this, and it will return a value between 0 and 1. And it will do a smooth transition. So it's a built-in function of AGSL, so we can just use it. I also use this mix function. This will linear interpolate between 2 input values. So we put in A and B, and we provide a weight between 0 and 1. And then it will interpolate between both values. We can also provide float 2, float 3, and float 4 values here. So then it will do this mixing for all channels or for all components of these vectors. Now let's apply this to our code. So first of all, we define a smooth size here, how long the edge is. And then in line 7, we add the smooth step to the distance function. And then I also have to subtract the smooth size from the radius, because otherwise the circle would be bigger than the canvas. And then I can define 2 different colors, background and foreground, and mix between both colors. Oh, sorry. When we change this variable from the smooth size, then you see the edges get more blurry. We can also make it smaller, and then the edge is more sharp. And when it gets too small, then we get this pixelation effect again. But you have a lot of control here. There are, of course, also other simple functions like rectangles, triangles, hexagon, and here pie shape. There's a nice source for these distance functions from Inigo Quiles. Here's a link. He also explains a little bit about the math. But yeah, for me, I just take the functions. So you don't have to have a degree in math to work with it. We can also combine then different shapes. For example, we could subtract 2 shapes from each other using the maximum. So therefore, we provide the distance of one shape, and then the minus the distance of the other shape, and then it will subtract the second shape from the first one. There's also when we want to have a union of two shapes, we can just use the minimum of both distances. And an intersection would be the maximum of both distances without a minus. Other possibility to do some things with the shapes is deformations. Therefore, we do not change the distance function itself. We only change the coordinate system. So, for example, when we want to move our shape in the x or y axis, then we just have to add x or y values to our coordinate system. We can also do scaling by multiplying by a factor. And here you can see a sample. First, I move the coordinate system to the center, and then I multiply, in this case, in the x-axis by 2, so 2, 1, and the first parameter of this float 2 is the x-axis. But yeah, maybe a little bit not so intuitive, but as you can see, it will reduce the width of our circle by half. Instead of when you use a multiply by 2, then the opposite, you multiply the coordinate system, and then the opposite will happen to our shape. If you multiply the y coordinate by 2, then it will be squashed in the y-x. So we can also do rotation. Therefore, we need to use a rotation matrix, a 2 by 2 matrix in this case. Also here, we of course need to move our coordinate system to 0, 0. And this 2 by 2 matrix, then we can multiply our coordinate system vector, the x, y vector, by this 2 by 2 matrix, and we get back a rotated vector or position in our coordinate system. I want to show you a sample. Of course, when I show a circle, then you will not see anything when I rotate it. So here I will use a box from this code from Inigo Quiles. And in my main function, we have still a canvas by 200 by 200, and the center position would be 100, 100. We go to the center in our coordinate system. Then, we have to provide the angle of the rotation in radians. So if you want to use degrees, then you have to convert this to radians. And then you just multiply our vector coordinate by this rotate function. And then this SD box will be rotated, as you can see on the right. We also can use here the smooth steps function to avoid these pixelated edges. Maybe you think it's very boring and we cannot do much with this. But here's a sample shader. So here I just use triangles and different colors, rotation, the smooth step function, and you can see we can get some amazing effects with it. The shader code is not so much. I defined a triangle function here with different parameters, and then I just fiddle around with different parameters here and draw a lot of triangles, and this is the result. So it's not much code. And this all runs on the graphics card, so it's very fast. So next chapter is animations. How can we do animations? Therefore, we use the built-in compose functions for animation. So in this case, I use this remember infinite transition and then animate a float value. Important here, I use an initial value of 0 and a target value of 1. This is better because the math is much easier in my shader code when I just have values between 0 and 1. And one other important thing here to consider is the the time of the translations. This is, it's important to define the easing function, linear easing, because otherwise the time could be distorted. And then we can use our uniforms to get this value, this animation value, into our shader code. So in this case, I use the variable iTime. And the shader code then, I have this uniform iTime, and I just use the same code like before, but the angle, I will use the iTime value. And as you can see, I multiplied it by 2 and pi, 2 pi, because 2 pi is exactly 360 degrees. So this makes sure that our rotation will not be interrupted at the end, and there we have an infinite loop. Yeah, I showed you this loading animation at the beginning. Here I do a little bit more things. So first of all, often it's helpful to convert the coordinate system to be between 1 and -1 and have a 0, 0 at the center. This does this line. And then we have the angle calculation here. And here we can also use for loops. In this case, I draw 24 different rectangles. Here I calculate the orientation for the rectangles. And then, I moved it out a little bit so it's not in the middle. And then I calculate an intensity. So the rectangle will not rotate, just the size, and this blur value will be changed depending on the intensity, as you can see here. So here's the size from the box, and here's the smooth steps also based on the intensity value. And then we add this all together in this luminance value variable. At the end, I clamp this value, so it's between 0 and 1, so otherwise we could get some overexposure effects, which I do not want in this case. And then we multiply everything by a float 3 with a color. So in this case, I used green, but of course you can use any color. And then we return this color. Okay, sorry. The other effect you saw is this shine animation of buttons. Here we do not need a rotation matrix. We can just tilt our coordinate system a little bit. So in this case, I just added the x and y coordinate together, but the y coordinate is multiplied by .4, so it's a little bit tilted. And then I use 2 smooth step functions. The first one is the starting edge of the shine, and second one is subtracted from it. This will be the end of the shine. And then we calculate a color out of it, and that's it. So it's just 19 lines of code. I showed you this shader before, and when you look closely, you see that there's it's also only rectangles and circles in this shader. So you can program this shader with the knowledge you get so far. Here's the code, by the way. It's just 31 lines of code. But of course, you have to fiddle around with the values a little bit to get this effect. So now we come to the development process itself. We all are used to this live coding thing from Android Studio. So when we change our compose code in the preview, we instantly see the changes, and also even when we run our app and change some shader code, it will show instantly the changes. This will also work for AGSL and for this runtime shaders. But the problem is often when we change the shader code, then it's sometimes in an invalid state. Or we do also make mistakes, and this would crash the app. So the solution would be to put a try catch around our runtime shader creation. and then check here if we created a shader or not, and only draw when there's a valid shader code. Yeah, here's a small live demo. It's not live because I recorded it, because I was afraid that something goes wrong. But here you can see the Android Studio preview, and at the right, a device where this shader code is running on a device. And as you can see, when I change the values, yeah, instantly we see the changes in the preview and also on the device. Yeah, I can also do animations here. Yeah, you see here that the preview is not animated now, but animations also work in the preview, but we have to manually enable it. So therefore, yeah, we have to click on this animation button. Yeah, now I do it here. But yeah, it's working, and you can also step through the different animation steps. So it's very nice. Yeah, so very nice integrated and working well in Android Studio. Here, for example, when we use as background an alpha value of 0, then you see the background. So let's talk a little bit about compatibility. So AGSL was introduced in Android 13 or API level 33, but it's also supported by Compose for desktop, and it's based on SKSL. SKSL is Skia shading language, and Android uses Skia to draw everything. Also, this is legacy UI, not only Compose. And SKSL itself, it's based on GLSL. It's OpenGL shading language, which is supported on almost any device, or even very old devices. So, yeah, maybe you already noticed it. Here I have this annotation requires API 33. If I do not want this, because I also would like to have apps, Android devices, older devices, well, I want to support older devices, then yeah, I have to check the version here before I create the runtime shader and the brush. And for example, I could just then use the solid color or some of the built-in shaders. Yeah, I played around a little bit with code, and I do have, yeah, it's experimental and in development. But I programmed a backport, more or less, so I'm using OpenGL and draw a fragment shader. And here you can give this pixel shader the same source like AGSL. And then you can draw something. But yeah, it's a little bit limited, because you cannot do it with a modifier, so it's only possible when we define a composable here. And of course, it's not possible in Compose. This code will use legacy views, so a surface view or a texture view. So it's a little bit more overhead. So you should consider, if you want to use it, do not use it on any place, because it's a little bit more overhead. But yeah, the code is here on GitHub. Okay, so now at the end, I will show you some ideas, some experimental things from me. For example, you could draw a pie diagram, and here, when I turn the phone, depending on the attitude, I will calculate the direction from the light, and then we have this shadow effects, for example. Just an idea, you can go creative. Or another thing is, if you want to program an audio player, for example, then you could have also create a shader to show the spectrogram like this. Okay, so that's it. So as you can see, it's possible to create amazing effects with AGSL. Using shaders at the right place makes your app outstanding because, yeah, not so many apps use shaders today because, yeah, it's a completely different language and it's very new in Android at least. Yeah, it's a bit of a steep learning curve, but as you have as you can see, you do not need a master's degree. And the most important thing, it's very fast, so it gets compiled and then executed on the GPU. But yeah, if you want just to draw some simple lines and circles and stuff like that, maybe it's easier to just use the Canvas Draw API. Here are some references of the source code. Yeah, of course, I only did not have much time today, so there's much more to this, what you can do. There are other YouTube channels. One is from Inigo Quiles. He goes also into the math a lot, and there's another one which I could recommend is The Art of Code. And what you should look to is the shadertoy.com website. It's a WebGL-based shader system. There you can directly program shaders in the browser. And it's a very big community, and you can see many different shaders. So have a look. Oh, thank you for your attention. Here's the QR code again, so you can have a look at the slides and my contact data.